A big part of the success of our economy attributes to robot. If you go to a modern industrial facility, you will see a picture like this. So that's an example of Tesla Motors. Hundreds of robots creating products at an incredible speed, precision, and endurance. But how many robots have you seen today at your home, on the way here, or even in this building? The reason we don't have that many robots here around is that they're simply not able to cope with the highly uncertain and dynamic environment we live in. An industrial robot is built in a very stiff, built and controlled in a very stiff manner to move objects along a predefined trajectory with sub-millimeter accuracy. And they have to do this independent whether they're carrying a 50-gram screwdriver or a 200-kilogram motor block. Now, these properties are great as long as you live in a deterministic environment, as you've seen before in this manufacturing and assembly line. However, it can become quite dangerous as soon as you start interacting with humans. And it can even be fatal for the robot if you collide with unexpected obstacles in its environment. In other words, if we want to create robots that are able to live next to us in our surrounding, we have to change the way how we activate and control them. Now, if you have a look at nature, we see that humans and animals are actually built not rigid like a robot, but very compliant. We have rigid links, in this case bones. But the compliance comes in from the activation. We have muscles and tendons, and that acts very elastically. And this provides us many different advantages while we're interactive in the environment, both during locomotion and manipulation. Our team took inspiration from these principles, and we realized an activation concept that is very similar to this muscle tendon system. We use electric motors and gears to drive the system, so similar to the muscle, that incorporate the spring between the gearbox output and the contact point to provide the necessary compliance to the system. Now, this compliance is deflected as soon as we get interaction with the environment. We can measure this deflection, which means that since we know the characteristics of the spring, we can get a pretty accurate force measurements at the contact point, and then we can use our motor to actively regulate this force. So with this, we made a change from a classical industrial robot that does precise positioning to a machine that is able to interact with the environment. As a proof of concept, we created Starlet. That's a four-legged robot that has 3 degrees of freedom per leg, all of them driven by the compliant actuator I've been presenting before. Starlet is able to run over different kinds of terrain. That's a typical trotting gait it's executing. You can do more dynamic gaits. This is bounding, where we have back and front legs in simultaneous ground contact. You can even start running. So here you clearly see that there is a big flight phase in the middle. And if you push it to the limit, you're able to jump. So for all these maneuvers that we're doing, we are exploiting the compliance of the system as much as we can. However, we still need to have accurate control. And this I want to explain with the real system here. So first of all, we're using a simulation tool to generate the desired behavior. In this case, it's a trotting gait. During the trotting gait, the robot has its diagonal pairs of legs in simultaneous ground contact. So it's only stabilized on a step-to-step basis. If we want to stabilize this motion, we first of all need to sense how the robot is moving. And for that, we implemented a sense of balance. So very similar to what we have in our inner ear organ, we implemented here an IMU and combined this information together with the kinematic readings that we have from the joint sensors to figure out how the robot is moving. Then we are balancing in 2 different ways. So first of all, with the legs that are stepping, we are doing steps according to the desired and the actual velocities and acceleration I have of the body. So if I push the robot to the side, you see that it's doing a side step. If I pull it to the other side, it reacts accordingly again. With the legs that are in ground contact, we are permanently doing an optimal force distribution using the full dynamics model of the entire system. To give you a little bit of feeling about the complexity of the algorithms that are here behind, these are a couple 10,000 lines of code that are running 500 times per second on this stack of pretty powerful onboard PCs. Of course, if you want to do something useful, so if you want to navigate around any kind of environment we need to see, for this we have mounted here in the front a laser sensor which is scanning the environment. So you see here on the screen what the robot is actually seeing at the moment. So the audience here in front of you. This creates about 50,000 points per second of the whole environment and can be assembled to full 3D elevation, full 3D representation of the environment. And if I'm standing here in the front, you see me waving the hand. All right. Of course, with this we have means in our hands to send robots to arbitrary places which have so far not been accessible for machines. In our research, we're tackling two different parts. On one side, we're mainly working in the search and rescue domains. On the other side, we're doing industrial inspections for offshore oil and gas platforms. The technology we're using here has proven to be pretty valid for all kinds of different robots to do interaction. So we started already 2 years ago to combine our controls, electronics, motors, gear springs, and sensor to very compact actuator units, which one of them I have already here. So these units are universal joints that contain all this information, which have all the different properties that we need to build robots that are well suited for interaction. This is one side, like we've seen in industrial robot, fast position tracking. We then have, in addition to that, very compliant and precise force control while interacting with the environment. So what you see here is really zero torque behaviors that can very compliantly interact with the environment. So we can also have impact robustness, so we can hit the output and it will not be destroyed, and finally have a very safe interaction. So if you're moving the machine and interact with a human, we don't destroy the machine. So this provides a tool for us and other researchers to develop all kinds of different robots that are meant for interaction, like robot arms or robotic dogs. I want to present to you today a very short teaser and quick presentation of the new generation of quadrupedal system we developed at ETH Zurich, which is all composed from this module. So it's only an arrangement of small modules, not a single additional gear or bearing, just kinematic structures and these modular devices. This machine is roughly 25 kilograms heavy. There's an onboard battery, and with that is able to run for about 2 hours completely autonomous. The big advantage of this machine is that we have a pretty large range of motion. So the machine is able to work in all kinds of configuration, can do different gaits, different maneuvers, and overcome various obstacles. Saying hello and welcomes you to the stage afterwards. Thank you for your attention.